Okay, and in this video I'm going to talk about diagonalization, and I'm going to give only an introduction about diagonalization in this video and the main properties that is going to be there whenever we say that there is a diagonal matrix. Okay, let's go and see what is the definition of the diagonal matrix and how we can work on it. First of all, the definition, recall that the elements a, I of a matrix make up its main diagonal. Okay, so whenever we have a matrix and we have these elements are making the diagonal of this matrix, then if they are non-zeros and the off diagonal other elements are zeros, then we call this matrix as diagonal. All other matrix elements are called off-diagonal elements, as you know. So this is, we call it the diagonal, and these are the off-diagonal elements. Okay, we call them off-diagonal. Okay, so if this diagonal, they are, first of all, the matrix should be square. So if a square matrix is called diagonal matrix, if all the off-diagonal elements are zero. So this is the first condition, that all of them, they are going to be zero. The off-diagonal elements are zero. And a diagonal matrix has the appearance as you can see here, which is, let's clear here. So these are the only elements that is having numerical values. Other ones, which are the off-diagonal elements, they are zeros. Okay, so this is considered to be the diagonalization definition, or the diagonal matrix shape or appearance, how it can appear. Okay, now let's go to the diagonal matrices properties, the properties of diagonal matrices, and why we want it, or why we are interested in it. Okay, diagonal matrices have many pleasant properties. Means that pleasant properties means that they are going to help us in our solution and analysis of the matrices. So whenever we can see diagonal matrix, it is going to make our calculation simpler, and we can tell, or we can solve our problem in a simpler way. Okay, let A and B be n by n diagonal matrices. So we are going to assume that we have A to be a diagonal matrix and B to be a diagonal matrix. As I said, here the elements are non-zero and everything here is going to be zero. The same here. Okay, here there are some elements and here it is going to be off diagonal are going to be zeros. Okay, with diagonal elements respectively A II and B II. So we have here all the elements to be like something like this: A11, A22, ANN, okay, and so on. So we are having it as if that is AII here for elements and BII here. So this means that the first element here is going to be like A11, as I said. The second is going to be A22, and so on and so forth. Okay? Okay. So A plus B, the first property that we can find for diagonal matrix is going to be A plus B is diagonal with diagonal elements AII plus BII. So this is very easy. Whenever we are going to add them up, we're going to find it is going to be very easy for us to do so, because at the end we're going to end with a matrix. This matrix is going to be like here A11 plus B11, for example. And here is going to be A22 plus B22, and here will be ANN plus BNN, and so on. So these are like the diagonal matrix as well. In a similar fashion, this is the second property. AB, which is the dot product of the matrices, diagonal matrices, is diagonal with diagonal elements AII, BII. So instead, if we are going to multiply them, I mean that dot product, for example, then we're going to find, let's clear here everything. So the product that is going to be there from A, B is going to be here A11, B11, and here A22, B22, and so on until ANN, BNN, right? Okay, so this is the second property that we are having that is related to the dot product of the two matrices, two diagonal matrices, and the previous one was related to the addition of both of them. So the elements of the diagonals are going to be super easy to be calculated for the both cases. Okay, another important property that is going to be important for us to know and use as well is the determinant. Do you remember how we calculated the determinant before? Exactly. It was a little bit taking time or a little bit time consuming process, especially whenever that we have a big matrix, right? That's right. That's true. So in our case, if we are talking about the matrix A, the determinant of matrix A is going to be easy to be calculated. It is going to be the product of the diagonal elements. So we're going to multiply the diagonal elements, all of them, okay, and then we are going to obtain the determinant. So A11 times A22 till ANN. Okay, so this is going to be super easy for obtaining the determinant. Okay, and from 3, A is non-singular exactly when each diagonal element is non-zero. Take care of this. If we assume that we have, let's clear here everything. So if we have A here, for example, and we have A11, A22 until ANN, okay? And I've told you that the determinant is going to be obtained from this equation, the multiplication of the non-zero elements along the diagonal. So we can, based on that, we can say that A is non-singular exactly when each diagonal element is non-zero. Because if there is one element here is 0 along this diagonal, we're going to have what? Zero determinant. This means that what? So A has non-zero. Yes, this is if we are going to have 0 element here, we are going to have our determinant to be 0, right? So this means that it is going to be singular. But if all of them they are non-zeros, this means that A is non-singular, and this is going to, we are going to say that A has non-zero determinant, right? So like a condition, like a prerequisite or a condition that we are having here, okay? The determinant and the singularity, as we have explained in the previous video. Okay, in this event, the inverse of the matrix A minus 1 is the diagonal matrix having diagonal elements of 1 over AII. So the inverse is going to be very simple here. If we're going to have the inverse of the matrix, it is going to be like yes, 1 over A11 here, 1 over A22, 1 over ANN, and so on. Very simple. So now we can obtain the determinant simply, and we can judge whether or not the matrix is singular or not, and in the same time we can obtain the inverse of the matrix in a very simple way. Look to these properties. They are very important, and they are going to make the calculation in many cases to be very easy and simple. Okay, now the fifth property is the eigenvalues of A are its diagonal elements. The eigenvalues of A are its diagonal elements. This is very important as well. So if A is diagonal, then the eigenvalues of this matrix are going to be the diagonal elements, A11, A22 until ANN, as we have mentioned. Okay, so now the determinant is easy to be obtained. The singularity of the matrix can be determined. Eigenvalues are super easy. We can obtain them because easily they are the diagonal elements, right? Okay, let's go to the last property that is going to be important also for us. If we are going to assume that A is a diagonal matrix, as we have mentioned before, only this diagonal is having non-zero elements and the off diagonals are having 0 elements, then the eigenvalues lambda I and the corresponding eigenvectors ei are given by, so eigenvalues, as we have said in the previous property, is going to be on the diagonal. This is already known, we know this. But what is going to be important for us is exactly the eigenvector. The first column here is going to be the first eigenvector, and the second column is going to be the second eigenvector, and the third is going to be the third eigenvector, and each one is corresponding to its lambda. So lambda 1, lambda 2, lambda 3, and so on. This lambda is going to be a11, and this is going to be a22, this is going to be a33, and if we have lambda n, then it is going to be a(n), and then we are going to have en, which is the eigenvector. Eigenvector here because the eigenvector is going to be the place where that the eigenvalue is. We are going to replace it with 1, okay, because they are multiplied, as we have said before. The multiplication, or the C, do you remember the CE is considered to be eigenvector as well, okay? Multiplicities, or not multiplicities, the multiplication or the non-zero multiples of the eigenvector is an eigenvector. I have mentioned this in the previous videos, okay? So this is very easy for us now. So lambda 2 is going to be corresponding to an eigenvector with the second element to be 1 here, and so on and so forth until we reach to lambda n, where that it has eigenvalue a and n, which is this value, and the corresponding eigenvector is going to be with 1 at the place of this at the last place of the elements, okay? So this is going to be our eigenvector corresponding to lambda n. We call it en corresponding to lambda n, okay? Okay, so these are the main properties of the diagonalization. And then let's go to another thing which is important. Again, I'm going to repeat because really they are important. Really they are important. The diagonal matrices are important for us because they are going to make our calculation super easy in many cases. Addition of diagonal matrices is just addition of their diagonal elements. Multiplication is going to be only by multiplying their diagonal elements. Determinant is going to be by the multiplication of the diagonal elements, all of them. And we can judge whether A is singular or not, okay, because we are not expecting any of these elements to be 0. If they are, or if there is one 0 element, then it is going to be singular, and there is no inverse in this case. But if they are non-zeros, then A is non-singular, and in this event A minus 1, which is the inverse of the matrix, can be calculated, okay? In this event, A minus 1 is the diagonal matrix having the diagonal elements A over, so it is going to be like this. A minus 1, as I said, it is going to be 1 over A11, 1 over A22, until 1 over A and n, and so on. It is very easy for us to calculate the inverse in this case. And number 5 and 6, they are related to one another. We said that if we have the matrix to be diagonal, the diagonal elements, they are going to be the eigenvalues, and the column of each, each column of the matrix are going to be the corresponding eigenvector. So this is E1, this is E2, and this is going to be E3, and so on. Okay, so each eigenvector is corresponding to its eigenvalue. So lambda 1 equals to A11, and the corresponding is going to be E1. Okay, and so on and so forth with the other ones. So these are very good and important properties for the diagonalization, or for a diagonal matrix. Let's go now to how to diagonalize matrices. So if we say that A is diagonal matrix, well, this is good, but who guarantees that A is going to be a diagonal matrix if it doesn't look like a diagonal matrix? We don't know. Maybe there is a way that we need to follow in order to transform any matrix to a diagonal matrix. And whether that this matrix is going to be diagonal, like diagonalizable or not, it is related primarily to some criteria that we want to discuss here. So first of all, we want to say that most matrices are not diagonal. So this is a fact that we need to believe in, okay? That most matrices, the majority of matrices, they are not diagonal, okay? They are not diagonal. However, sometimes it is possible to transform a matrix to a diagonal one, and this is what I've said, okay? We can. There is a way to transform the matrix to a diagonal one. This will enable us to transform some problems to simpler one. And this is here the key, that if we could tell that this matrix, we can transform it to be diagonal matrix, everything is going to be easy for us. We can obtain its inverse easily, we can obtain the determinant, we can judge whether it's singular or not, okay? We can know its eigenvectors, we can know its eigenvalues. Everything is going to be easy for us, right? So it is important to know whether or not the matrix is can be transformed to diagonal matrix or not. Okay, now let's put here the way or the definition for how to tell whether a matrix is diagonalizable or not. Transformed to be the diagonal matrix, okay? An n by n matrix A is diagonalizable if there is an n by n matrix P such that P minus 1 or inverse of this matrix times A times P dot product, okay, is a diagonal matrix. In this case, we say that P diagonalizes A. P diagonalizes A. Like if we have like a matrix A and we are not sure whether it is diagonal matrix or not, so we are going to get a matrix called P and we are going to make dot product, okay, like this on A. If the output of this dot product is going to be a diagonal matrix, okay, if it's going to be a diagonal matrix, only non-zero elements on the diagonal and the off diagonals are going to be zeros, then in this case we say that A is able to be transferred to diagonal matrix. It is diagonalizable, okay, diagonalizable, okay. So anyway, this is how it is, like the way of how judging the matrix to be able to be diagonal matrix or not, okay. We're going to obtain matrix called P, and this P we are going to have this P minus 1 times A times P in order to get the output. If it is going to be diagonal matrix, then A is able to be diagonal matrix, okay, otherwise no. Okay, so we will see that not every matrix is diagonalizable, and the following result not only tells us exactly when A is diagonalizable, but also how to choose P to diagonalize A, and that P minus 1 A P must look like. Okay, we are going to tell this in the theorem. Bear with me because next time I'm going to talk about, or I'm going to give examples, so everything is going to be super easy later on. Just now I want you to bear with me to understand what is the meaning of diagonalization of a matrix means, okay, as a theorem that we need to follow. Okay, let A be n by n matrix, then A is diagonalizable if and only if A has n linearly independent eigenvectors. Furthermore, if P, so this is number one, we have linearly independent eigenvectors. This is like a condition that we should take care. They are linearly independent. Okay, what is the meaning of linearly independent? If we have like 1, 2, 3 in one column, and the other column is like 2, 4, 6. So it is seemingly we can look to this and say that, well, this column, this eigenvector, equals to 2 times the other column, which is 1, 2, 3, right? So this is like, there is linear dependency here. Linear dependency here. So we are talking about the case where that we cannot get this linear dependency, the case where that A has n linearly independent eigenvectors. The columns are not repetition of one another or multiplication of one another. Furthermore, so this is the first condition. Furthermore, if P is the n by n matrix having these eigenvectors as columns, okay? If P is the n matrix, n by n matrix having these eigenvectors as columns, okay? So let's assume that the eigenvectors P is going to have like the eigenvectors E1, E2, E3, and so on. Like everyone like a column here, like eigenvectors. If this P, if we assume that n by n matrix having these eigenvectors as columns, then P minus 1 AP is the n by n diagonal matrix having the eigenvalues of A down its main diagonal. So we are going to have P minus 1 AP is going to give us a matrix. This matrix are going to give us the elements here are going to be like, this is A11, A22, A33. These are the eigenvalues. These are the eigenvalues, okay, of A down its main diagonal in order in which the eigenvectors are chosen as column of P. Okay, this means that if we say that P is having E1, then the corresponding here is A11. So the first element is going to be A11 here. Okay, and this one, the corresponding eigenvalue is A22. Then here this is going to be A22, right? And this one is A33. This means here it is going to be A33, and so on. So in the same order, it is important. Okay, so let's clean everything, and let's say that this is like we are like as if we are flipping this part, we are putting it here. Okay, the condition on Q, which is the P, the matrix B that we're going to use. So in addition, we say if Q is any matrix that diagonalizes A, so we are sure that Q is diagonalizing A, this is assured, then necessarily the diagonal matrix Q minus 1 AQ has the eigenvalues of A along its main diagonal. That's true. Okay, it is like as if flipping the previous one. If we have Q, we are sure that A is any matrix that diagonalizes A, then necessarily the diagonal matrix Q minus 1 AQ has the eigenvalues of A along its main diagonal, and the columns of Q must be exactly eigenvectors of A in the order in which eigenvalues appear on the main diagonal of Q minus 1 AQ. It is, as I said, like flipping this. If we are going to tell that we have this matrix that we are sure it diagonalizes A, then these kind of consequences we are going to face. Okay, I think that it is enough now to talk about this, and I think that we need to have some examples on how we can diagonalize matrices and whether that this condition is going to be fulfilled for all matrices or not. This is going to be in the next videos. Okay, till then, see you, and I wish that you could have understand what I have explained in today's video. Thank you, and see you next video.